full screen. Is it okay this way? Okay.
Yes, very good. Are you ready?
Yes.
Okay, so welcome everyone to the last SPD semester of this semester. Our speaker today is Aurélien Deya from the Institut Élie Cartin in Nancy, France. Aurélien is a specialist of rough path theory, stochastic PDEs, and fractional processes. And we're very happy to have you here today and look forward to your talk titled Nonlinear PDE Models with Stochastic Fractional Perturbation.
Oh, thank you very much for this nice introduction. And of course, thank you for the invitation. I'm very pleased to give this talk. First of all, I have to say that what I will talk about is based on a series of works. And for some of those works, I got help from some of my colleagues in Nancy. First, Nicolas Scheffer, my PhD student, and also two colleagues, Laurent Thoman and Renaud Marty. And even if those various works involve different settings and different techniques of analysis, they were all concerned with the study of a nonlinear PDE that we perturb with the stochastic fractional noise. And so my objective in this talk will be to survey those results and try to encompass them into a single presentation. Let me introduce this dynamics. Here it is. So this is this equation. So PDE model that we perturb with the stochastic noise. So in the end, this is a stochastic PDE model. We study it on 0t times RD. What is it made of? First, on the left-hand side, you have the linear part, the linear operator. And here, we can be quite flexible. I mean, in the sequel, we will be able to handle three situations. First, when L is the heat operator, GTU minus delta U, where delta is just a Laplacian, of course. And in this case, you have to specify the value of U at time 0. Then we can also consider the wave operator case. Okay, and in this case, you have to specify both the value of U at time 0 and the value of DTU. And finally, there will be the Schrödinger operator case, I DTU minus delta U. Of course, the results in each situation will not be the same, and even the approach and the technical arguments will not be exactly the same. But overall, the strategy and the main ideas will be very similar. So this is what we can encompass those three a priori different settings into a single presentation. So this is for the left, and on the right-hand side, you have two terms. First, the nonlinearity, U squared, nonlinear drift. Okay, and I will go back to this a bit later. And finally, you have the noise. And here, this is probably the main specificity of this work. We wanted to go beyond the classical white noise situation and handle a space-time fractional noise. I'm aware that this fractional noise setting may be not the most standard framework. And so for this reason, let me briefly recall what a space-time fractional is. I mean, what we refer to as a space-time fractional noise. To do so, let's remember that a possible way to define the white noise is to start from a Brownian field and then take derivative in time and in space. This is a possible way to define the white noise. And here we just follow the same idea. The only difference is that instead of starting from Brownian sheet, we start from a fractional Brownian sheet, or a fractional Brownian field. Okay. So what do we call a space-time fractional Brownian field? Well, it's a family of fields that depends on some parameters, h, the Hurst index, and actually it's a vector of indexes, h0, h1, ht, 0, 1. And once you fix those indexes, the space-time fractional Brownian field of index h is the centered Gaussian field on 0t times Rd with covariance given by the product of the fractional, the usual fractional covariance, which is this function here for h in 0, 1 defined for a and b and r as 1/2 of a to the power 2h plus b to the power 2h minus a minus b to the power 2h with absolute value. You may know that this is indeed the covariance of a standard one parameter fractional Brownian motion. And so here we have the natural multi-parameter extension of the fractional Brownian motion. with the product of the covariances. And as you can see, we associate each successive index with each successive variable, okay? So H0 is for the time variable, then H1 for the first space variable, H2 for the second space variable, and so on. And those indexes may be different, okay? We really have a fractional noise in every direction, and the indexes may be different. So in the end, we have a quite flexible family of processes at our disposal. And now, as I say, to define the space-time fractional noise, we take derivative in time, and also derivative in space. Okay, just as we do it to define the white noise. And just as with the white noise, and as you can guess, the fractional Brownian field is not something differentiable. So the derivatives here can only be understood in the sense of the distributions. Okay. I will comment further in a few slides about our choice of the fractional noise, but maybe the first point to emphasize is that in the specific situation, when you take all those indexes here equal to 1/2, you may know that in this case, the fractional covariance coincide with the usual Brownian covariance, which means that in this situation, the space-time fractional Brownian field is just the standard Brownian field, and when taking derivative, we recover the classical space-time white noise situation. So we are working with a natural fractional extension of the white noise situation. Again, I will comment further on our motivation behind this noise in a few slides. But now let me briefly go back to the dynamics and try to highlight some possible basic motivations. So let's start very basic level. And what we can say here is that there are, well, two possible ways to see the equation, two possible approaches. On the one hand, you can see this as the most basic stochastic perturbation of a classical nonlinear PDE, LU equal U square, okay, which is part of an important family, the PDEs with power nonlinearities. Okay, and here indeed we have the most basic stochastic perturbation because we only consider an additive noise. And then you can also take the reverse approach and see this as the most basic nonlinear extension of a well-known stochastic PDE, okay, LU equal B dot, a linear stochastic PDE, LU equal B dot. And the solution of this is explicitly known, okay? We know that morally the solution is given by the convolution of B dot with the green kernel, or the fundamental solution associated with L, okay? We know that if we can give a reasonable sense to this convolution, and I will go back to this a bit later, then this provides us with an explicit expression for this, an explicit solution for this well-known stochastic PDE. Of course, when you add the square, there's no explicit solution anymore. And finally, we can see this dynamics as a first step toward more general and maybe more physically relevant fractional Hamiltonian PDE, where the nonlinearity is made of the product of U with the absolute value or the modulus of U to the power P minus 1. Okay, here we can somehow see this first model as the case where P equal to 2, at least if you don't care about the sign of U, so at least locally in time, let's say, okay. But of course, in the future, we would like to extend the arguments we've developed for this model to this general situation. Okay. Now, why considering a fractional noise? What are the motivation instead of a classical white noise? So first, we've seen that fractional noise is more general than a white noise, okay? So the fractional analysis is an extension of the white noise situation. We're not completely leaving the stage. And also, you may know that as soon as we deviate from the Brownian situation, which means as soon as the Hurst indexes are different from 1/2, some important properties are lost. Some martingale type property or Ito type isometry property, okay, they're no longer available when working with a fractional noise, I mean, except in the white noise situation. And so it's quite interesting to see whether we can do without those techniques and if we can still handle the equation. But even more importantly, when working with a fractional noise, we can very sharply control and very sharply study the influence of the roughness of the noise on the equation, because the roughness is known to be governed by the parameters of the fractional noise. The idea is that the smaller of those parameters, the rougher the noise. Okay, and so by letting those parameters vary, we can calibrate the roughness of the noise and study the transition between various situations. Okay, so the idea usually is to start from the regular situation where the parameters are close to 1, and in this case, the noise the field is almost a well-defined differentiable function, so the noise is almost a well-defined function. Okay, and so in this case, we somehow in the almost in the regular PDE setting, okay, with classical PDE setting with well-defined functions. And then you can let the indexes decrease and study the transition with rougher situations, such as the white noise situation, or even rougher situation if you want. And we know that in most cases, something is to occur in this transition. Okay, we know that usually we cannot handle the equation with the white noise as we do it with in the regular case. Okay, so something is to happen in this transition, and we can study this phenomenon. We can also make the link with another well-known situation, which is the case of a white noise in space. We know that this somehow corresponds to taking H0 equal to 1 and all space indexes equal to 1/2. Okay, so by letting the indexes vary, we can study in some continuous way the transition between those well-known situations. And of course, there are many intermediate fractional situations of great interest as well. Okay, so this is the idea, and this is what I will develop in the sequel for this particular model. And as we'll see, and as I've already evoked it, we will see some interesting change of regime phenomenon. I mean, when we see that when the indexes are close to 1, we're in the regular situation, and we can treat this equation with quite direct arguments, which means a direct interpretation and a direct solving procedure. But then when you let the indexes decrease, so the noise becomes too rough, and at some point, direct treatment is no longer possible. We have to turn to more sophisticated arguments and expansions of the equations and possibly renormalization trick. Okay, so this is what I will develop in the sequel. This change of regime phenomenon is already something we can see in the white noise situation. But in the white noise situation, for this to appear, you need to change dimension. Okay? For instance, you may know that in the white noise case, in the heat situation for L, and when D is equal to 1, we can provide a direct treatment. But when D is equal to 2, then we need to involve renormalization to understand this equation is in the white noise setting. Okay, so this change of regime is already something that can be observed in the white noise case, but for this, you need to change dimension. Here, you don't need to change dimension. You only let to let the indexes decrease. Okay, so in some way, this is a smoother transition. Here, when you change from D to D+1, this can be quite brutal when working with a fixed white noise. Okay, so at least partially understand my motivation and my enthusiasm for considering fractional noises. And so this is what we will develop in the sequel. But before I go into a little more detail, I have to specify one technical point, just to be completely honest. As we've seen, the equation is stated and will be studied on RD. This is RD in space. And at first sight, this can be considered as quite ambitious because, of course, RD is a non-compact domain, and we know that this may give rise to a few painful considerations when trying to control the behavior of the processes at infinity in space. This can be quite technical. And to be honest, for the moment, I'm not fully able to study the equation as I previously formulated it. What I'm only able to study is this localized version of the equation with an artificial cutoff trick in front of the nonlinearity. Okay, so a function of space that is smooth with compact support. We can take this function arbitrary. I mean, it can be equal to 1 on any compact domain. So we consider that at least locally, the dynamics is still satisfied. And thanks to this cutoff function, we can bring the analysis on RD back to compact domain. Okay, so this is the idea. Of course, again, in some future work, we hope to get rid of this artificial cutoff. I cannot hide it, but we know that a standard way to proceed is to involve weights in the topology, in the space topologies. And given the relative sophistication of our arguments, we fear that this might be a quite difficult task, but okay, we still need to work on this. But now you may wonder why we consider the equation on RD and then use this artificial cutoff trick to go back to compact domains instead of just considering the equation on a compact domain from the beginning. The reason is the noise, okay? Because as we've seen, the fractional noise is something easy and natural to define on RD, okay? Just take derivative of a fractional Brownian field. Whereas fractional noise on torus, for instance, is something more subtle. And as far as I know, there is no general consensus about such a definition on the torus, okay? So I prefer to work with this more natural noise. And also, the fractional noise on RD is something that has been extensively used during the last few years in many papers about other fractional SPDE models. I mean, other SPDE models involving a fractional noise, such as the parabolic Anderson model, for instance. This can be found in many papers by Chad Chen, Yao Zhonggu, David Nuala, Jian Song, Sami Tardel, and others. And they all use this noise, this fractional noise on RD. So here, considering the very same noise, somehow make a link with this literature and it allows us to compare the assumptions on the parameters of the noise that we can cover with the analysis. Okay, so this was another motivation for considering the equation on RD, and then for technical reasons, go back to compact domain with a cutoff function. This being said, in the sequel, and for the sake of clarity, I will not insist on this row dependence issue. Okay, I will not even indicate the presence of row, because as we will see, we will be led to expand the equation at order 2, order 3, and if you explicitly write down row in those expansion, then the expression become very, very cumbersome and just illegible. So I prefer to get rid of this row and focus on the main arguments. But please keep in mind that the analysis actually takes place on compact domain, even if the equation is stated on RD. Okay, well, I think I'm done with this long introduction, and now let's go a little more in detail with this analysis. The starting point of the analysis is the mild formulation of the equation, as is often the case. Okay, we rephrased it in terms of a convolution with a green kernel G. And this gives 3 terms to analyze on the right. You have first the initial condition term, which is a convolution in space at fixed time with the green kernel and with the initial condition. Okay, this is for the heat and the Schrödinger situation. In the wave situation, you certainly know that you also have to involve a second initial condition term, okay, with the convolution with the derivative of G. Okay. Then you have the space-time convolution of G with the nonlinearity U square. And finally, you have the space-time nonlinear convolution with the noise, B dot. And I will refer to this as the linear solution, because this is indeed the solution of the equation when you remove the square and with 0 initial condition. So I will call it the linear solution. Of course, for the moment, we haven't solved the equation, but at least with this formulation, we can try to make some guess about what will be the roughest term of the equation, the one that will govern the regularity and ultimately give the regularity of U. And this is important because this will tell us in which space we can study this equation. So let's have a look at the 3 terms. In this presentation, I will always assume that phi is a regular initial condition, so smooth with compact support, just to simplify, which means that this element, this first term, will always be very regular. And from here, it's easy to guess that the roughest term will be the last term here, because remember that B dot is expected to be a very rough. Okay, so this clearly will yield the roughest term of the equation, and U is expected to have the same regularity as this term. Okay, so first, our first challenge in this story is to get a sharp control on the regularity of this linear solution, because this will again indicate us in which space we can study the equation. So this is the first objective. This is the first thing we need to do. Unfortunately, even if this looks explicit, the study of the linear solution is not completely trivial due to the roughness of the fractional field. And even the interpretation of this convolution is not completely clear, because B dot is a distribution, I mean, very rough distribution, and G is a green kernel, so it's a singular function, even possibly a distribution. So even the convolution here is not something immediately given by the theory of distribution. We have to think about it. And so we are somehow facing a double challenge here. We need to find suitable interpretation and then get sharp control on the regularity of these elements. To do so, we have relied on some standard approximation or regularization procedure. Okay, the idea is always the same. When we don't know how to define something due to an irregularity issue, we go back first to the smooth situation and then try to pass to the limit. So this is what we've done here. We've considered an approximation, smooth approximation of the field. Then we defined a smooth approximation of the noise by taking derivative in the classical Lebesgue sense. And when taking convolution with G, we get a smooth approximation of the linear solution. And from here, what we would like to study is whether this can converge as n to infinity. Okay, if we can find a suitable space where this sequence converges, then the limit will give a natural definition for our original convolution. Okay, to implement this idea, we need to introduce an approximation. And for this, again, we've turned to standard procedure, a modifying procedure. Okay, we take convolution of B with a modifying sequence based on regular test function rho. Okay, something that converges to a direct mass. And so we start from this, then define B dot n using standard derivative, and finally get our sequence of solution. And we want to study this sequence. And here is the scale of spaces we've used to study this convergence issue. So those are the spaces of continuous function of time, okay, on 0t, with values in a fractional Sobolev space for the x variable, okay? And more precisely, we've used this definition of fractional Sobolev spaces, okay? So this is the Bessel potential spaces, I think. Okay, and as you can see, this depends on the derivative parameter alpha and also on some integrability parameter here. We take integration in LP, but for the sake of clarity, I will not indicate the P dependence in the sequel, because otherwise the statement becomes too cumbersome. I mean, there are already the Hurst parameters to handle, so I try to reduce the number of parameters at the minimum. Okay. So this is the scale of spaces we've used. In the heat situation, this may be not the most clever choice. I mean, not the sharpest choice. If you know about regularity structures, then you know that in the developments there involve some kind of homogeneous space of spaces where time and space variable are somehow considered at the same level. And this allows to include elements that are distribution in space, but also distribution in time. And here, this is not the case. Okay, here we're working with elements that can be distribution in space, but that are function of time. So this is less flexible than the topology used in regularity structures. But on the other hand, in the wave situation or in the Schrödinger situation, and given the arguments we used and the techniques used therein, I think this is the most natural choice. And since we want something that could encompass the three settings, okay, the heat case, wave case, Schrödinger case. We're somehow stuck to this scale of spaces. Okay. Now from here, I think the objective is quite clear. Now we need to find a suitable alpha here, suitable value, for which this sequence of approximated linear solution can converge in this space. This is the objective, and here is what we get in this direction. We can indeed identify such a value for alpha. More precisely, we can get a threshold, alpha dh, such that if alpha is strictly smaller than alpha dh, then the sequence converges almost surely to some limit in the space I've introduced, okay, continuous function of time with values in W alpha. The value of this threshold here depends on the dimension D. It depends on H, the Hurst index. Remember that we're working with a fractional noise governed by indexes. And it also depends on G. Okay, so it also depends on the operator we are working with, whether the heat, the wave, or the Schrödinger. In the heat situation, we get this exact value, 2H0 plus H1 plus H2 plus HT minus D. And in particular, you can see how the scaling, the parabolic scaling echoes on the linear combination. Okay, we know that time somehow counts twice, and this echoes on this 2H0 because H0 is indeed the time Hurst index. Okay. Then in the wave situation, we have this value H0 plus H1 plus H2 plus HT minus D minus 1/2. Okay, there's no parabolic scaling anymore. Time and space are considered at the same level. And finally, in the Schrödinger case, we have 2H0 plus H1 plus H2 plus HT minus D plus 1. And here you can see that the solution in the Schrödinger case is less regular than in the heat situation. And indeed, this is something we could expect because we know that the regularizing effect of the heat semigroup are stronger than the one of the Schrödinger kernel. Okay, so this is the kind of result we can show with stochastic arguments. Okay, the idea is to control the moments of this sequence with suitable topology, and then use some kind of a Kolmogorov type criterion, okay, to get almost sure convergence. And this threshold is sharp. Okay, we could not do better. At least in this scale, we could not improve the regularity. This is what we can prove. And now from here, well, we see that there will be two very different situations to be considered in the sequel. The first situation is when this value here, alpha dh, is positive. And indeed, you see that if the Hurst indexes are not too small, okay, so if the noise is not too rough, then this value, alpha dh, can be, well, it's positive. So this means that we can pick alpha positive. And in this situation, the linear solution can be seen as a function of time, but also as a function of space. Okay. Then there will be the other situation when you let the indexes decrease. At some point, those values become negative. Okay. And in this situation, we can only consider the linear solution as a function of time and as a distribution in space, negative order distribution. And this will considerably change the analysis of the equation. But let's first have a quick look at the regular case, okay? The positive case where alpha dh is positive, so the indexes are not too small and the noise is not too rough. And this is what I call the regular situation, because in this case, the solution, as I said, is a function of time and also a function of space. Now remember that U is expected to have the same regularity at this element. So U in this case is expected to be a function of time and a function of space as well. And this is of great interest because if U is a function, then we have absolutely no problem with the interpretation of the nonlinearity. U squared here, in this case, it can just be considered as a standard product of function, pointwise product of function. So we have absolutely no problem with the interpretation of the equation, and we are immediately in a position to set up a fixed point arguments. And so this is what we've done by using the properties of G in each case. we've been able to prove that, so this is deterministic. For here, this is the deterministic step. The previous stochastic step is over. And so we proved that indeed, the equation admits a unique solution in the space under consideration, at least for a small time t. For the moment, we've only focused on local solution, but given the square, we have no clear hope to get a global solution. But for this to hold, I mean, for this fixed point argument to work, we sometimes need to impose restriction on the dimension d. And this is because we still need to control the square in this equation, okay? Based on the properties of G. In the heat situation, then there's no such restriction. We can take, we can solve the equation for any dimension D, and this is due to the very nice properties of the heat semigroup in this case. But then when it comes to the wave situation or the Schrödinger situation, we need to assume that D is smaller than 4 in each case. And this can be seen as a consequence of the Strickhaus inequalities, the inequalities that give a very sharp control on the action of G in the wave situation or in the Schrödinger situation. Okay, but for this to work and to control the square, we need D to be smaller than 4. This restriction is already something that occurs in the deterministic case, okay, when there's no noise, there's no linear solution here. So we clearly have no hope to relax this assumption on the dimension, at least with those arguments and using this scale of functions. Okay. So this is a brief summary of the results we got in the regular situation for the heat wave Schrödinger kernel, Schrödinger operator. And now let's turn to the more interesting negative case where alpha dh is negative, which I call the rough case. And in this situation, we've seen that the linear solution can only be treated as a negative order distribution in space, okay? And of course, this immediately confronts us with a major interpretation issue because U, again, is expected to have the same regularity. So U in this case is expected to be a distribution, a negative order distribution in space. And if U is a distribution, then, well, okay, it's not clear how we can give a sense to this U square. This can no longer be interpreted as a product, pointwise product of function. This interpretation no longer works. And so we have this new first challenge in comparison with the regular case about the interpretation of the square. To help us, we can rely on some quite classical trick, which is the D'Aprato-Debush trick. And this consists in looking at the equation satisfied by a new process, V, defined as U minus the linear solution. Okay, we subtract the roughest term, the linear solution, and look at the equation satisfied for V. Here is this equation. It's not difficult to obtain. You just have to put the linear solution to the left, which is V, and then you replace U in the U square with V plus the linear solution, and you expand the square, okay, which gives those three terms. And the first idea behind D'Aprato-Debush trick, I mean, the first hope is that thanks to the properties of G, V may be more regular than U. Okay, we expect V to be more regular, to be some kind of remainder, okay? And possibly we could go back to a space of functions where if we go back to a space of function, then we won't have any problem anymore with the interpretation of this V squared. This is the first hope using D'Aprato-Debush trick. But of course, at first sight, we still have an interpretation issue in this new equation because again, the linear solution is a negative order distribution, so we still have to cope with the square of a negative order distribution, and it's not clear how to interpret such a square, such a product. So at first sight, we haven't made any real progress in this analysis. In fact, there's a huge difference between the two problems. I mean, between the square here and the square here. The huge difference is that the linear solution is something explicit. I mean, it's something we've explicitly constructed in terms of the noise. Okay, so morally it should behave as a Gaussian process. Well, okay, it's not a well-defined process, but it's the limit of Gaussian process, so it can be quite flexible. And this is very different from U here. The solution U is only, well, very implicitly defined. I mean, it will be defined as a solution of a fixed point argument, so very abstract definition. And so much less tractable than the linear solution. And when it comes to the study of this question of how to interpret the square, it will be much, much more convenient to work with the explicit linear solution than with the implicit U here. So this is the second advantage of this formulation using the Daprato-Debush trick. Okay. Now, with those considerations in mind, the strategy goes as follows. First, we have to deal with this square, how to interpret this square. And for this, we will be able to rely on a stochastic renormalization procedure. And once endowed with this square, then indeed, we will be able to solve the equation in a suitable space, in a space of function of time and space. Okay, and this is due to the properties of G. So let's first look at the interpretation of the square. And here, we have no choice but to turn to a renormalization procedure. A direct definition here would clearly not be possible. So we have to turn to renormalization. To implement the method, we go back to the smooth situation. Okay, we introduce the smooth field Bn, the approximation, then B dot n is the derivative, and you go back to the, in this way, to the smooth approximation of the linear solution. So now for fixed n, this is a well-defined Gaussian process. And when working with Gaussian processes or in Gaussian cases, we know that there's a quite standard renormalization procedure, which is the Wick procedure. And here it just consists in subtracting the expectation of this square that I denote by sigma n. Okay, so the idea is that in this well-defined product, okay, in this well-defined square for fixed n, if we only consider this square and try to let n tend to infinity, this will explode. This will not converge. But when subtracting the expectation, and thanks to the nice simplification that occur in Gaussian cases, we hope to catch some limits. And this is indeed what happens, at least in some situation. Okay, we can show convergence of this sequence of renormalized square, okay, almost sure convergence, in the space of continuous function of time with values in W2 alpha, with alpha satisfying the same condition as before, so smaller than the threshold. And indeed, this is the topology we expect in this case, because if alpha satisfies this condition, we know that the linear solution is in W alpha. So it's not a surprise that its square be in W2 alpha. It's a standard phenomenon in this distribution situation. But for the moment, we can establish this convergence if the roughness is not too small. If alpha dh, the coefficient that governs the roughness of the linear solution, is not too small, and more precisely when it's larger than -1/4 in each case. Here, of course, the exact value for alpha dh has not changed. It's just the same as before. I've just rewritten it in each case just as a reminder. But what is important is that this new condition in this statement, for this convergence to work, we need alpha dh to be larger, sorry, than -1/4. So this may, and it is quite restrictive. I cannot hide it, but well, first it shows that at least in some cases renormalization works. This is our first. We were quite happy to observe this, and when looking closer, as we'll see in the next slide, this still covers some very interesting situation, okay, for the Hurst indexes and for the exact definition of the noise. But what I can say now is that this restriction here, larger than -1/4, is clearly not something optimal. I mean, here we wanted a condition that could hold for every dimension D, okay, so we had to deal with many variables, many fractional kernels, many Hurst indexes, and so at some point in the computations we've lost sharpness. Okay, but when looking at more simple situation, when D is equal to 1 or D equal to 2, we can refine the estimate, the stochastic estimate, And in those more simple situations, we can handle some cases where alpha dh is smaller than -1/4. Okay. Nevertheless, what we can also say is that this convergence does not hold for every value of alpha dh. If the noise is too rough, then at some point convergence fades and it will no longer be possible to use this renormalization trick. So for instance, in the heat situation, we have this result that tells us that if alpha dh is smaller than -d/4, then you have this explosion phenomenon here for the second order moments in every sub-F space. You may choose alpha as small as you want. This will explode, okay? And this can be turned into almost sure non-existence result for the renormalized square, okay? And we have a similar statement in the wave situation, at least when equal to 2, but it could certainly be extended to every d. So again, here we know that if alpha dh is smaller than some value at -1/2, then it will not be possible to use this renormalization trick, okay? So we have those quite interesting phenomenon that tell us that if the noise is too rough, then the method will not work. It will not be possible to renormalize the square, and this approach will not work, at least not with this scale of spaces. Okay. Well, anyway, what we can retain for the sequel is that at least if the noise is not rough, we can use a renormalization trick to define the square in the renormalized sense from this linear solution. Okay. Once endowed with the square, the stochastic analysis is over. We can turn to the deterministic fixed point arguments. Remember that we focused on this equation for V, and in this equation, we replace the ill-defined square with a well-defined renormalized square. So here again, we can set up a fixed point argument by using the properties of G, but we need to impose restriction on D and on alpha as well, okay, the regularity of the linear solution. In the heat situation, no restriction on D, okay, no problem with the square, but alpha here cannot be as small as we want. We need alpha to be larger than -2/3. And indeed, remember that here our objective was to go back to a space of function. And if this guy here and this guy here, whose regularity are governed by alpha, if they are too rough distributions, then the regularizing effect of the heat semigroup will not be sufficient to go back to a space of function. So this is why we need this restriction on the roughness of the noise. We need to go back to a space of function with the semigroup. Okay. In the wave situation, we have still the same restriction on D due to the control of the square, and again some restriction on alpha for the same reasons, and this can be seen from the Strickard's inequalities that give the regularization properties of G. And the situation is even worse. In the Schrödinger case, we need D to be smaller than 3 and alpha very close to 0, because here Strickard's inequalities are not sufficient to regularize the noise, to regularize the elements, the square, and here the linear solution. We have to turn to even more specific local regularization properties, and this requires alpha to be very close to 0. So again, this appeared to be very restrictive, but when looking closer, we realized that it still covers some interesting situation. For instance, if you take dimension 2 in the wave and heat case and consider the white noise situation, which corresponds to all indexes equal to 1/2, then you can check that the coefficient in this case is precisely 0, okay? And this means that in this situation, this important situation, we could not rely on the previous regular statement. We really need to turn to this theorem and this renormalization trick, okay? And in the Schrödinger case, you can compute that when d is equal to 2 and when you're working with a white noise in space, so this is h0 equal 1 and h1 is equal to 1/2, then again, the coefficient is 0. So we need this statement to solve this, to solve the equation in this important case. And of course, there are other intermediate fractional situations of great interest. Okay, well, I think I will soon run out of time, so let me just skip my next slide or about the possibility to get expansions of higher orders. Let me just say very briefly that indeed we can, in some situation, we can repeat and we can iterate the Apparato-Debus trick and expand the equation at order 3 instead of order 2. And naturally, this gives rise to new tree elements, more sophisticated tree elements to be properly defined with a renormalization trick. And then we can set up a fixed point argument based on the properties of G. So this, it turns out that in some cases, this can be implemented. This works in some heat situation, wave situation, and it allows us to deal with an even lower value for alpha DH. Okay, so it allows us to include even rougher noises in the analysis, more a value of the Hurst indexes and rougher noises. Okay. Now, in the remaining minutes, I just would like to say a few words about what I've been working on for a few months, which is the possibility to discretize those fractional models. At least we've looked at the very first step of it. Let's focus on the standard one-dimensional heat situation as far as L is concerned, just for simplicity. And what I would like to do in this new study would be to emphasize within a discretization scheme the central role of the pair made of the linear solution and the renormalized square. We've seen in the theoretical part that those two elements, the linear solution and the square, were the keys toward the study, I mean, the interpretation and the solving procedure. And so my objective would be to emphasize this phenomenon within a discretization scheme, okay? Exhibit a discretization scheme relying on those two elements. Well, at least this is the general objective. But to be honest, for the moment, we've only looked at the very first step of this project, which is the discretization of the linear solution itself. Because before we can discretize and possibly simulate U by relying on the linear solution and the square, we need to be able to discretize and possibly simulate the linear solution itself. And it turns out to be already not easy at all. So let me explain why this is clearly not easy. We don't want to do things halfway in this story. We really want a full discretization scheme, something that we could concretely implement. Not only discretization in time or discretization in space, really full discretization, which requires discretization of the noise and then discretization of the heat operator in time and in space, okay? Let me briefly evoke a few reasons why this is not easy. First, we want this analysis to cover the interesting rough regime, okay, when alpha DH is negative, which in this case is 2H0 plus H1 smaller than 1. And we've seen that in this rough situation, the linear solution is expected to live in a negative order suborder space, which means that we will need to control the discretization, the approximation, using negative order suborder topology. And this clearly contrasts with many, well, most existing results in the approximation literature, where authors typically focuses on well-defined processes, and typically they use the L2 norm to control the space. Here, this is not possible because the process is too rough. We need to involve suborder norm, negative suborder norm in the controls. Then the other problem is that we're working on a non-compact domain. We're working on R. Okay, there's no cutoff trick for the linear solution. And again, this can be occasionally painful. And the grid we consider in space, the discrete grid, this discretization procedure, needs to grow to infinity, okay, if we want to catch the actual solution. And as a consequence, at every step of the analysis, we need to control the behavior of the approximation on the border of this grid. And this can be occasionally painful. And again, I've realized that this is clearly not the most standard setting in the theory of the approximation of SPDs, where authors essentially focus on equations on a bounded domain, okay, with suitable boundary condition. And last but not least, we're working with a fractional noise and not a white noise, and this makes computations more technical, just as in the theoretical part. There are many simplifications that are no longer available in this case. Okay, so for all those reasons, I've soon realized that this the situation we try to handle is very different from any existing setting in the SPD approximation literature. Well, at least I haven't found a similar setting. Of course, I wouldn't have time enough to develop those various points, but still let me try to briefly review the main steps of the analysis. So we want full discretization, which first requires discretization of the noise. And this is done in two steps. First, we have a necessary smoothing procedure. Before we can discretize, we have to smoothen the noise. And this can be seen as a reminiscence of the fact that the linear solution is defined as the limit of a smooth approximation based on a smooth noise. Okay, this is precisely the smooth noise. So this is why we need this first intermediate step. Once endowed with the smoothing, then we can turn to discretization over some grid of size 1/n. Okay, and by discretization I mean we approximate the derivative, space-time derivative of the field with increments. Okay, 2D increments of the squares of this grid. This is for the noise discretization step. And then you have discretization of the heat operator. And for this, the idea is just to adapt standard techniques used in PD theory. So for space discretization, I've used a Galerkin type procedure, okay, which consists in projecting the equation on some basis of elementary functions. Small l here is for the size of the support of those functions, and capital L for the number of those elementary functions. And then you have time discretization. So here we've used an implicit Euler scheme. I've discovered that explicit Euler scheme do not work well in the PD setting. So we've used implicit Euler scheme over some uniform partition of size 1/m. And the m here can be different from the n here, the grid used for the noise. And so in the end, if you combine those successive steps, you get indeed a fully discretized approximation that can be expanded as a linear combination of the elements in the basis. Okay, and the coefficients satisfy this elementary iterative formula. And in the end, what we only need to simulate are the variations of the fractional field. Okay, and this is just a Gaussian field with a well-known covariance. Okay, so it's not difficult. And of course, we can justify this approximation. We can justify this scheme. It does converge to the actual solution, okay, in the space W alpha, as we expected it, with alpha negative in the rough case. And for this, you just need to find some suitable calibration of all those parameters. So the K parameter for the smoothing, then N parameter for discretization of the noise, then the small l, capital L, and the small m here. So you have to find a suitable way in the estimate to leg this, but it can be done, and it works. So in the end, we have something we can concretely implement. And here is what it gives. For instance, in the regular situation when the indexes are quite close to 1, okay, and indeed, in this case, we expect a function of time and space, and this is what it looks like. And then we can switch to the rough situation where the indexes are very low, okay, we're in the rough case, and indeed, this clearly looks like a distribution, okay. So I think I will stop with those drawings, and it only remains for me to thank you.
Thank you very much for this very interesting talk. Other questions from the audience? maybe I'll go first. So I have a question about the topologies that that you consider. So you consider the topology given by the continuous functions in time with values in some Bessel potential spaces. So my question is, does it make sense to consider spaces with different, regularities in each dimension or each direction? Because I think your noise is also, has different regularity in different dimensions. So
yes,
does
absolutely.
it make sense?
You mean, for instance, introduce some regularity in time?
Yeah, alpha 1 to alpha d or alpha 0 to alpha d, also in space for each spatial coordinate a different index, because your noise is also different in each direction, right?
Oh no! Once you consider the about the space first, this alpha here, when you consider the convolution with the noise, with the kernel G, then the indexes can no longer be differentiated. I mean, they all mix together in the computations, and so as far as space variable are space indexes are concerned, you get this combination that appears immediately, and the indexes just appear through this combination here. Now, as far as time is concerned, yes, this is certainly possible. For instance, to introduce Hölder regularity in time, a Hölder coefficient, but well, when I say it's this is true for the heat situation. In the heat, I mean, all depends on the arguments you used in the determinist in the fixed point arguments. In the heat situation, this is certainly possible due to the action of G. But in the wave and the Schrödinger case, which were actually the cases we were the most interested in, I'm not sure you can get some Hölder regularity due to the shape of the Strickhardt inequalities. If you look at the Strickhardt inequalities, which is the arguments we've used for the fixed point arguments, this cannot provide us with any Hölder regularity. Where with the action of G, this is, no, we're working in LP spaces, L infinity spaces, and well, or maybe we should do a further study once endowed with the solution. But for the fixed point arguments, no, we're not. This is not something given by the Strickhardt inequalities. But maybe some further analysis of the regularity once endowed with the solution. It may be possible. Okay.
All right. Thank you.
But this means that this alpha, if we put some Hölder regularity in time, this alpha should certainly be smaller. We should lose some time. We should lose some regularity in space. This is
right.
The usual phenomenon.
Are there further questions?
May I ask, why are you working in these LP-based spaces instead of perhaps you consider them the typical XSP spaces for the Schrödinger equation, for instance? Is there any advantage to this, or?
You mean this scale here?
Yeah, like in the Schrödinger equations, you might consider something like an XSP space instead of
the Bourgain spaces, you mean?
Yes, exactly.
Oh, yes, absolutely. But again, we wanted to a scale where we could compare the different situations, and this is why I've chosen the one used in the wave situation. I think this is clearly the most usual. Am I wrong?
Yes. Yes, I was just wondering for.
And since I wanted to compare, we wanted to compare those conditions, typically those conditions here. This is why we've used the same scale, but maybe we could get sharper results with the other scales, with Bourgain space in the Schrödinger situation. And the same is true for the heat situation. As I said, if we had worked with the topologies used in regularity structures, then maybe we could get some more flexible spaces and try to handle even rougher situation. Well,
I see, but the goal was to compare.
Yes, the idea was to compare in each case.
I see. Thank you.
You're welcome.
Further questions? I have one more. So do you know anything about long-term behavior of your solutions?
No, honestly, given the square, I do not expect a global solution. But
yeah, so does the solution blow up at some point?
Yes, this is what we expect, but for the moment we haven't proved it. But indeed, this is what we expect in the square situation.
Right.
But well, maybe the cutoff, but again, we would like to get rid of this cutoff in the next step. But maybe with the cutoff, there could be some global solution. I'm not sure about it, but maybe.
So in your statement now, so the statement is more like there exists a T such that you have the solution, right? It's not for any given T.
The solution here, no, what I'm only able to prove is that there exists a solution on a small time interval 0 to 0.
Right, so there exists a capital T. There exists a capital, okay, good, okay.
Yes, but I haven't exhibited any explosion time or any global solution.
Right. All right, are there any further questions? If not, let's thank the speaker again.
Thank you very much.
So this was the last SPD seminar. So probably we'll have other SPD seminars in the fall. So thanks everyone for joining. Bye-bye.